TXRX Systems has been producing equipment for use in land mobile radio, LMR, since 1976. Products are used to enhance the receive characteristics of base station and repeater sites to give portables, mobiles, and handhelds better range and capabilities, to reduce the number of feed lines on the tower, reduce tower loading, to monitor power levels and feedline health, and many other applications. Section 1 of this material will cover the equipment used at sites. TXRX Systems has a long history with transmit and receive site equipment and offers some of the most advanced and reliable components available. This training module will cover the basics of site systems, technology, and application. More detailed information will be included in the next sections. This section is an introduction to LMR site equipment and will include the topics listed in the index here. For quick reference, you will find the following at Towers and sites are covered on slides 3 and 4. Site infrastructure equipment are covered on slides 5 and 7. Transmit and receive basics are on slides 8 through 10. Combiner and multicouplers are covered on slides 11 through 14. Duplexers are on slides 15 through 16. Antennas, feedline, and monitors are on slides 17 and 18. A summary slide is included on slide 19, and contact information will be found on slide 20. Direct line of sight, uncluttered communication paths would be ideal for land mobile radio, but seldom happen. Tower sites are often located on hilltops and building tops and use the additional height to get better coverage. Many sites are crowded, packed with towers, or the towers are covered with antennas. Sites are seldom single-use sites, being only LMR, and are almost always a combination of commercial, cellular sites and public safety co-located on the same site and towers. Tower owners discuss and rent vertical real estate. Towers also come in many shapes and sizes, from simple monopoles to very tall freestanding structures or guide towers. For many applications, one of the first rules is that the taller the tower, the greater the coverage. In the United States, many commercial television and FM radio towers are built at or slightly above 2,000 feet, or 609.6 meters, to gain large coverage areas. The tallest towers are usually mast towers that are strengthened by guy wires, held up to withstand the force of the wind against the tower, transmission lines, antennas, and other components mounted on the tower. The Not in My Backyard or NIMBY movement has created a market for monopalms and monomaples, towers disguised to look like trees, making them more aesthetically pleasing to communities. Additional height can also be gained by mounting antennas on building and water tower tops. Careful planning is required on these installations to be sure that antennas, all at the same height, do not cause interference or degradation to other systems, using horizontal and frequency separation rather than vertical separation to get enough isolation. Tower and site design are based on multiple factors, but the starting point is coverage. Coverage is how far you want your signals to go. Land mobile radio and cellular telephone are considered point-to-point communication, one radio talking to one radio and then responding through the same system. Many factors impact coverage, and digital communications has changed things somewhat, but the basic principles of radio communication remain the same. One of the first considerations is transmitter power output, or TPO. The higher the power, the further the signal goes. Most land mobile radio transmitters are 100 watts or less. Antennas are passive devices, meaning that they do not have amplifiers as part of their design. They are a piece of wire in their simplest form. They can appear to amplify the signal, resulting in higher effective radiated power in the coverage area. Antenna gain is actually the redirecting of signal power in the coverage area, but the result is improved or increased coverage. Height above average terrain includes how far up in the air the antenna is and what the ground surface around the site is like. Flat, hilly, mountainous, city. The higher the antenna is above average terrain, the larger the coverage area. Lower frequencies are attenuated less with distance than higher frequencies, giving VHF and UHF LMR greater coverage than 700, 800, or 900 MHz systems. System gains and losses include tower top amplifier systems, transmission line loss, connector losses, antenna gains, filter losses, and any other contribution to signal gain or loss. TXRX systems assist with system balance. Balance is the optimizing of the system in the uplink and downlink paths, or talk in, talk out. Coverage is not about maximum power, but about clear, understood communication and requires proper setup. During these training modules, we will cover antennas, filters, combiners, duplexers, tower top amplifiers, receive multicouplers, and transmission line and connectors. Lightning protection, fencing, tower lighting, equipment room, site power supply and backup systems, grounding, data connections, cabling, installation, licenses, and other topics will not be covered. Early public safety radio systems used only one channel or a limited number of channels and needed only one antenna for what was called simplex communication. One antenna was used for both transmit and receive, with one transmission line. Systems were simple and sites were simple as well, but one channel wasn't enough. Current systems have between a few channels and 30 or more channels in larger cities. Different frequencies are used for transmit and for receive channels, doubling the required number of antennas. The illustration on the slide is not an accurate picture of what the tower would look like, as it would be taller, with the transmit antennas further up the tower. As is shown on the two pictures, feed lines cannot be installed with sharp bends and are usually installed at the corners of the tower near a leg. The two tower pictures show that there would be considerable wind resistance due to the number of antennas and the number of feed lines on the tower. This tower has a lot of structural steel to support the weight and wind plate area on the tower. Different geographical areas have different levels of average sustained wind and winter icing levels, and towers and antenna are rated to meet those specifications. Areas with high average wind ratings, such as mountain regions, also have different clamping or attachment specifications in order for equipment on the tower to survive. Grounding is also extremely important on towers and is specified by tower height and other factors. Static discharge on tall towers can be quite extreme, and care must be taken when climbing. As shown, the number of antennas and transmission lines can be significantly reduced by using combiners and receive multicouplers. For this system with 5 transmit and 5 receive channels, only 2 transmission lines are needed on the tower and only 2 antennas. Not only does this reduce the equipment purchase and installation expense for the site equipment, it greatly reduces wind and ice loading and the structural requirements of the tower itself, making it less expensive to install and to maintain. Nothing improves with time on a tower. Transmission lines deteriorate due to wind, rain, ice, snow, and even sunshine. Because of the heating and cooling of feedline during the daytime and nighttime hours, and the difference in the internal temperature of the feedline, it breathes, blowing out air during the day and bringing in cooler, moist air at night, resulting in water in the lines as well as pressure differences. All connections must be properly waterproofed, but even the best degrade over time, allowing water to enter. Water and RF do not mix and result in system deterioration. The reduction of the number of components on the tower through the use of combiners and receive multicouplers reduces the risk of system failure. Repeater sites are set up to allow the users to communicate with each other as well as with the base site. Transmitter repeaters are also called transceivers and allow for a great deal of flexibility in a system. As discussed previously, the use of transmit combiners and receive multicouplers at sites greatly cuts down on the number of antennas and transmission lines at the site, resulting in a lower cost of installation, use, and maintenance. Also, as previously noted, balancing the system at repeater sites is critically important. The combiner allows all transmit channels to be placed on a single transmission line. There are practical limits to how many channels can be carried by the feed line or input to an antenna, so be careful not to exceed power limitations. The receive system, whether using a TTA or a receive multicoupler or not, must protect the receiver front end from being overloaded, destroying sensitivity. Balancing is critical. Land mobile radio is a constant battle on the receive side. Close to sites, close to towers, reception will be fine, but as portables, mobiles, and handhelds move away from the base or repeater site, reception could falter, and emergency response radio users need strong, consistent communications. Transmitters are basically big amplifiers. Receivers are not. Receive systems are noise limited, and the subscribers in the system are power limited compared to system transmitters. Several very basic conditions limit land mobile radio and all radio communications. Free space path loss is the loss created by the distance between the transmit and receive antennas in an uncluttered RF path, which seldom happens. Anything in an RF path between transmit and receive antennas either reflects or absorbs RF energy, creating multipath signals or reducing received signal strength. Almost everything produces RF noise of one type or another. The receiver itself produces noise. Although it doesn't make sense that a loss produces noise, any reduction in signal while the system continues to produce noise is effectively the same as an increase in noise and is known as noise factor or noise figure. Keep in mind that on-channel noise cannot be filtered. Properly installed, properly optimized, and properly used, a TTA helps overcome the increase in noise and the losses sensitivity. TTAs from TXRX systems are more than an amplifier in a box on a tower. This diagram shows that land mobile radio systems are called upon for a great deal more than they ever have been in the past. LMR radios have expanded to include data and monitoring, video, and what is now known as a body area network with body-mounted cameras and telemetry. The primary use of first responder radios in emergency conditions is voice communication. Most modern systems have two additional IP networks. One of the networks is for control of the radios themselves, and a second is for monitoring the radios and systems such as shown on the diagram. Coverage in the system is based on factors already discussed, including ERP, height above average terrain, and losses and gains in the system, such as the use of a TTA. The higher the antenna on the tower, the larger the coverage area, but the longer the transmission line and the higher the line loss. The TTA is used to overcome the feedline loss of the system, effectively moving the receiver up to the receive antenna. The diagram shows that the RMC in this system is used to feed multiple systems or computers as well as system receivers. P25 Phase 2 diversity systems have begun deployment in many areas. These systems require the doubling of all RF components on the receive side, twice the number of receivers, antennas, and transmission lines in the receive network. While this is currently a single major LMR equipment provider system, it has been shown to improve receive sensitivity by combining two receive signals, resulting in higher gain. As with all digitally encoded signals, there is no signal fade in P25 Phase 2 TDMA. The signal is either there or it is not, what is now known as cliff effect. As with all systems moving forward, channel width is being reduced through a series of moves known as narrowbanding, going from 25 kHz channels to 12.5 and 6.25 kHz channel width or center spacing. The majority of systems in use are still non-diversity in either analog or digital modulation plans. Narrowbanding is still a requirement in all non-diversity systems and results in more channels available in the same amount of spectrum. doubling the number of channels, or adding the ability for the same channel spacing to carry more data. TX-RX combiners are used at communication sites to connect multiple transmitters to one feed line and one antenna. This helps reduce tower loading and the impact of ice and wind on the tower and equipment mounted on it. Many towers are loaded, supporting all the antennas and feed line that they can under local wind conditions. TXRX Systems designs and builds combiners which put the output of multiple transmitters onto one feed line going to one antenna. A combiner also acts as a filter to reduce unwanted transmitter noise. All amplifiers produce noise which is added to the signal. The combiner reduces transmitter noise and protects receive frequencies from that noise. Several factors are used to measure signal loss in a combiner: cavity and cable loss and bridging loss. Cavity loss is how much of the signal is reduced as it travels through a cavity. Bridging loss is how much energy is coupled or bridged into adjacent channels. By adding cavity loss to bridging loss, design engineers calculate the insertion loss of each channel going through the combiner. Cavity combiners are manufactured of many different materials, including aluminum tubing and copper sheet material. The combiner shown takes up less rack space and is easier to install than some of the larger cavity combiners. It has less points of failure and lower loss due to fewer cables, components, and connectors, with all parts being integrated into one unit. These combiners are easier and more cost-effective to maintain and expand. With the site powered, install any expansion cavities. Remotely tune with the tuning mode on the integrated power monitor using nothing but the base station and a PC. The combiner is set up in a star junction configuration, able to tune any frequency in any channel within range, and other existing cavities do not need to be retuned when new ones are added. The integrated power monitor is frequency selective for measuring power levels. The power monitor allows software configuration of alarms, identifying issues before they become big problems through remote continuous monitoring of forward and reflected power, test modes, antenna viswar, and both equipment and shelter temperature. The combiner comes in expansion modules of 2 cavities each with extra channels untuned until needed. This slide illustrates a UHF dual-band combiner receive multicoupler system that is available for order as a set-in-place rack system. As shown, this is a pre-configured 6-channel UHF dual-band transmit combiner and a 6-channel dual-band receive multicoupler system just needing interconnect cables. The system also includes a dual-band transmit filter for improving isolation in UHF applications. The filter response graph shows the dual band receive isolation given by the system. Deciding which type of control deck is needed for a system is important and must be done correctly. Control deck selection is based on what type of receivers are used. Radio manufacturers arrange the receivers in 2 different methods: systems which distribute the received signal to multiple receivers, and systems which need multiple feeds to individual receivers. TXRX provides control decks for both types of systems. There are several different names for control decks, but we will follow industry standards in this material. The simplest system is a base control unit, which feeds one output connector to a system with one input connector. The unit performs several functions, including supplying operating power to the tower top unit. DC voltage and current are fed to the tower top through the primary feed line, so all parts of the system must be maintained properly in order for the TTA to operate. The tower top unit connects through the feed line to the control deck, which is then connected to the receiver cabinet or cabinets. The receiver cabinet feeds the individual receivers. A base distribution unit has multiple outputs feeding individual receivers. The number of output ports is typically built for 8 or 16 connections, but can be expanded to 32 or more if needed. The deck will have amplification on board to overcome the coupler loss and feeds operating power to the tower top unit. Control decks and tower top units form a system when used together, but a TTA may not be needed in all applications. TTAs are generally used in 700, 800, and 900 MHz systems, but only when transmission line loss is greater than 1.5 dB. TTAs are not typically used in VHF and UHF systems, but receive multicouplers are designed for lower frequency systems and are used to preserve system sensitivity. A duplexer is made up of cavity filters, interconnect cables, and a coupler or junction. Using filters that pass the uplink and downlink channels with enough separation to maintain isolation, the duplexer immediately reduces the number of antennas and feedline on a tower. Duplexers can be built for a single transmit and receive pair feeding the antenna, or with enough channel separation can be used with 2 transmits and 2 receivers. Original duplexers were very simple passive devices. In order to maintain receive sensitivity and overcome feeder loss, duplexers are now built with low noise amplifiers in the receive side and with a hybrid design in the transmit side, allowing for their use with minimal transmit frequency separation. Milled bandpass aluminum filters result in superior isolation. The units are smaller and yet have higher power handling characteristics and very low PIM specifications. As in all duplexer installations, care must be taken not to try to push too much power through the duplexer, which usually results in guard bands being compromised and noise increasing, including PIM. As in most things RF, more power does not always result in improved system performance, and often exactly the opposite happens. Things start to go bad as the power increases. The number of antennas and transmission lines on the tower can also be significantly reduced using duplexers. For this system with 2 transmit and 2 receive channels, only 1 transmission line and antenna are needed on the tower, reducing equipment cost and installation expense. It greatly reduces wind and ice loading and the structural requirements of the tower itself, making it less expensive to install and to maintain. TXRX Systems and Comblent produce a series of duplexers offering several different approaches. Traditional duplexers are passive devices made of small cavities. With the required channel separation, the filters are tuned to pass both transmit and receive channels. Models are now offered with an amplifier in the receive path as illustrated on the circuit diagram, allowing sensitivity to be maintained or even improved. As shown, newer models are built using bandpass milled aluminum filters, resulting in compact designs, lower weight in the rack, and low PIM ratings for the units. Installation of the duplexer is simple and quick. Transmit outputs go to duplexer inputs, and receiver outputs on the duplexer connect to the receiver inputs. A single antenna connector is used for both transmit and receive. Tower sites include many pieces of equipment both on the tower and in the equipment shelter. Antennas and transmission lines are passive devices, but will have major impact on coverage. Signal distribution is controlled by the type of antenna used, the pattern, gain, and down tilt. An antenna is a piece of wire hung in the air, but the fields and interaction of those fields is complex. The antenna interacts with any metal nearby, including other antennas, guy wires, cabling, and clamps, and the tower itself. Proper installation guidelines, including standoff or mounting requirements, must be followed carefully. Many sites have many antennas and many services using the tower, and the technician must be careful on co-located sites both when performing service and for personal safety. Coaxial feedline or transmission line is designed with 2 surfaces inside that must maintain their spacing or their characteristics will not meet spec. Because of this, installation and waterproofing must be completed very carefully. Connectors must be installed properly using correct cutback and assembly tools. Clamping to the tower protects the cable from wind and ice damage, and the proper hangers must be used based on wind conditions in the area. Water will always find a way into feedline, but the goal is to keep it out, so be very careful with waterproofing. Grounding and lightning protection need to both follow required codes. Towers are part of our everyday lives in land mobile radio, and nothing gets better over time when mounted on a tower. Transmission line connectors, ground kits, lightning arresters, clamps, and mounting hardware, nothing improves with age on a tower. Weather is relentless with wind and ice and rain battering the lines. Ground vibration, wind, and tower movements work the feedline and the mounting clamps, and over time, the feedline deforms. The center picture on the right side of the slide shows a hospital roof near New York City with feedlines strewn across the grates, many with footprints on them. That installation job did not follow any standard practices and resulted in multiple problems. TXRX Systems and Comblent US have models of the Digital Power Monitor DPM available for all LMR bands, VHF, UHF, 700, 800, and 900 MHz. These monitoring units may be installed as standalone units or as integrated into filters, combiners, duplexers, or other components. Each DPM will monitor up to 10 carriers at 50 watts each, reporting forward and reflected power, insertion loss, antenna return loss or VISWAR, and operating temperature. Digital power monitors allow remote monitoring through user-friendly GUI displays over Ethernet and SNMP connections. Remote power monitoring units enable the end user to see the health of their transmission line and system. A great deal of thought and engineering go into site design, both before and after the site is up and operating. Nothing is left to chance when first responder and public safety lives are involved. Once the coverage area is clearly defined, the number of sites needed will be established, dependent upon factors such as frequency range of the system, the topography of the area, and a host of other factors. Tower locations may be limited to existing structures or to available property. Height, tower type, and other considerations are now part of zoning and planned communities and regulations. Transmitter power output and antenna selection will have a major impact on coverage. Frequency planning includes what is currently in use, what is in use nearby, and other carriers in the area that represent high power threats. TXRX Systems has been working with first responder systems since 1976, providing infrastructure products such as combiners and duplexers, antennas, and tower top amplifier systems. A leading innovator in custom solutions in VHF and UHF, TXRX, now paired with Comblent AS, an international corporation, produces radio infrastructure equipment for several major OEMs in the LMR industry and has capabilities to work with you and your team to design and supply your infrastructure equipment. TXRX Systems has a full-time staff of field service engineers and technicians ready and able to assist in solving your site issues. Before the design work begins or after the problems start, TXRX Systems and Comblent are here to help you with your site needs. Thank you for being part of this training module, for inquiring about TXRX systems and services, and for being part of our technical community. This section was intended as an introduction to land mobile radio equipment and systems. More training modules are available in support of this and other topics specific to products manufactured by TXRX Systems. The material is available in short versions and in longer half-day, full-day, and two-day classes. Visit our website at txrx.com for more information. Titles and topics are being added weekly, so please come back often to see what is available. Classes are available at TXRX Systems, 8625 Industrial Parkway, Angola, New York, or if your group or shop is large enough, we will bring the training to you. Please call 716-549-4700 to discuss fees and scheduling. Again, thank you for being part of this presentation, and we do invite you back.